Okay, there's no need for me to introduce the last speaker because it's me. This is not my talk. I'm presenting this on behalf of Jovan Silic, Rod Patterson, Des Fitzgerald, and I'll be talking about 2D, 2.5D inversion. So why might you want 2.5D? Well, 1D has a batch of artifacts, and particularly when the section, whoops, this thing is, can you back up to the, thanks. Okay, let's try again. There seems to be a timer on this I wasn't expecting. 3D needs lots of unknowns. You don't actually collect 3D because things are changing quite quickly. I won't try again with that. The dangers of other people's presentations. I didn't do that when I looked at it before. Okay, so this particular model, there was a number of model validation tests run by Geoscience Australia over a number of things to provide some assurance that the solutions were correct. And I'll just show one example of this is with the saltwater wedge over more resistive basement. This was modeling the SkyTEM 312 system. The saltwater wedge is shown in blue, and those are responses in X and Z components from the model, and similar responses from the high moment, and that was compared with known results and showed the system seemed to work. Now, I won't get into the mathematical formulation for the system, basically because I don't understand it. You'd need one of the authors to cover this for you. So, however, it's a somewhat different formulation with similar things. I'm not even changing the slides. This is just going. Okay, we have an example of some spectrum data in the Bryce Basin. There's, I think they decided I would only get 10 minutes. And geology, apparent conductivity. There's just a few lines across this with conductive. Okay, so this is just an example. So what you'll see in the plots, the colors of data, the predicted responses in black. This is an early iteration where they're very different. And in this case, the conductive model is nothing actually like fitting the data. There's various parameters which control how well you want to fit the data. That sort of particular thing decreases during it, but not going to get into that. Okay, so the first big advantage of 2.5D is it uses both the X and Z components. A 1D model can only fit the Z component from a central loop system because there is no X component from in a central loop system. So stitched 1D models can't fit any of the X component data. So this is an example of fitting Z component data to a model. Just taking Z component only, it's a reasonable fit, and it's showing a conductor in the middle within a dipping horizon. If we use X component only, again, you can actually fit that response, and you'll get a somewhat different look at what's in the middle. But actually, if both X and Z are used, you end up with a good fit to both X and Z components, and a very reasonable model. In this case, it was one of a syncline, which is what was expected. So in the central part of the section, using both components and a 2.5D model mapped a far more sensible geological model than either the X or Z alone. Okay, so just some examples of results from this. The top is a sort of 2D section, just of some again sort of spectrum data, showing up additional additional features, a shale horizon that was previously unknown, and a deep paleo valley. Okay, a couple of examples of 2D inversion over known deposits. This is a 2.5D inversion of data, and this is mapping a dipping conductor here, and that's sort of pretty much exactly agreeing with the position of the real drilled conductor. So it was a very sort of clear demonstration that that things were in the right place compared to the drilling. So the 2.5D was measuring in this case. Okay, so another data set. On this particular case, it's just comparing different inversions of the same data. 1D on the top, 2.5D on the bottom, showing some dipping features. A layered earth 1D underneath, the Geoscience Australia one, and at the bottom a 3D inversion. And of these, the 2.5D was the most sensible because they were known to be dipping graphite conductors, so certainly that inversion was consistent with geological expectation. This is an example of detecting a conductor on a long survey line. So this, I think, this is part of a 40-kilometer long line. We've got some responses to the right, and if we look at that particular thing, because this is so long, it's a bit blown up, that particular anomaly, the 2.5D inversion detected the LOE's body in the inversion in the correct place from the data and separated out the differences. This bigger response is overburden. So that bigger response is overburden, whereas that very much smaller, more subtle response is what ended up being the correct place. So that was an example of very good mapping. An example from Laylaw, that's the 2.5D conductivity inversion, showing again a nice synclinal look to it. I don't know the geology, so I won't comment on these 3D maps, on that 3D map. Okay, so the final bit is sort of examples of this algorithm in mapping water and near-surface conductivity. This is a case from Peace River, Alberta, and this is comparing SkyTEM data inverted with laterally constrained inversion at the top and the 2.5D at the bottom. And there's a few places, such as there's a very strong break in topography, so there's very big topographic effects that the 1D algorithm broke down, and the 2.5D gave a very big improvement, and ended up in sort of handling the effects of topography very sort of much better than conventional 1D. That's Marcus break. Okay, so the conclusions from work done to date is that 2.5D inversion can add significant accuracy and detail, even when a 1D assumption is mostly met. This was the case in the last slide. 3D structures are well imaged in 2.5D inversions. Not all 3D structures, obviously, but many of the ones tested. The 2.5D inversions do not suffer from loss of resolution common in 3D inversions. The trouble with 3D inversions is you have to have 100 times the number of sort of pixels. And so they can be very useful to invert data on sort of survey scale. And also for many Airborne EM surveys, line spacing is a lot wider. The resolution between lines is much less than along the line, so that sensible 3D is often not really good, just because the conductors don't necessarily, there's not sufficient data to come up with a full 3D model. The time penalty between 1D and 2.5D inversions is high, but the Intrepid team have make full advantage of parallel architectures, and get quite high speeds for this. So the evidence is that this 2.5D modeling can be useful. And whoops, this one. And I think that's it. I trust you're applauding the authors of the presentation rather than the presenter. Any questions? Not that I can guarantee to answer. Daniel. It's an old 3D inversion, which never worked particularly well. That is not a good example of 3D inversion. I've seen other 3D inversions that don't. What's odd, one of the things I have noticed is the worst 3D inversions do very badly on small targets. The reason is they've got to make big pixels, otherwise they get too many pixels. And when you have small, thin targets, 3D inversions give the worst possible result of anything. 3D inversions do a fantastic job when you have large targets, where you have, you're attempting to get details of the edges, where what you're trying to image is realistic on the scale of the voxels you're using. This is one of my pet bugs, is that if you have the reason they call it 2.5D is they have a 2D model and a 3D source. They've got a 3D source, because you've got your local equivalent, and a 2D model, so they've called it a 2.5D. Now, if you happen to have a 1D model, a layered Earth, and a 3D source, you don't call that 2D. So, averaging the two things is completely illogical, but nonetheless, it is a historical thing that slipped into the literature, which stands for 2D model and 3D source, as opposed to because straight 2D, there used to be quite a few straight 2D models had line sources rather than dipole sources. So it's bad arithmetic. The data certainly fits extremely well. From what I've seen, there's absolutely no question that in the cases I've seen, the model appears to be correct. It fits the data, it fits both X and Z to quite high accuracy. So I personally have no doubts as about whether it's sort of providing valid solutions or not. There are many cases, all EM solutions are ambiguous. The things in data that can't be fitted by data. So as far as I have no reason to believe that it's not providing solutions that are consistent with the data. Okay, well, thanks everyone for coming to the last session. And I'll tell Des and Jovan that they should have come and given it themselves, because they predicted there'd be no one here to see their talk.